Hello guys, this is 5.1. We're going to look at a very important idea in linear algebra, which is the eigentheory. Eigentheory is just a general name for what we're going to see here. So 5.1, we are going to focus on eigenvectors and eigenvalues. Now, before we actually get into the definition of those, let's start with an easy introduction. Let's look at linear operator. All right, so if you look at the top of 5.1 notes, you'll see that an operator is linear map from a vector space to itself, right? So we can say that, okay, there is a map T, right, that sends, let's say, V to V, okay? So whatever value you put in here, let's say little v, right? Some vector v in here, and then it's going to give you t of v, which is still in the space v, right? So both the vector v and t of v, they are both in the space v, and then we can say that t is a linear operator. Okay? Now, an operator that has this property is also called invariant. Under t, right? Because t sends a vector into the same space. Okay. Now let's look at the second paragraph. How does an operator behave on an invariant subspace of dimension 1? So subspaces of V of dimension 1 are easy to describe. Let's say we take any non-zero vector u. Right? Let's say we take u is in V, and let capital U be the set of all scalar multiples of little u, right? So capital U is equal to some scalar a times u, such that a is some real numbers. Right, then here we can say that capital U, is a one-dimensional subspace of V. Because what we're doing is we're just taking items in V and then multiply it by some scalar, right? So every one-dimensional subspace of V is of this form, which is just a scalar multiple of a vector in V. All right, and let's keep going. If U is in V, let's say if U is in V and capital U defined the same way, is invariant under some map T that sends V to V. Then here we can say that TU must be in capital U. Okay, so let's stop here and take a look at what we're saying here. Now we know that every one-dimensional subspace of V is of this form, right? Some scalar multiply the vector U. Okay, now let's say we introduce another operator, since V from V, then T of U must be in capital U. This is because T of U, that's also one-dimensional. Right? Taking this one-dimensional map, a linear map, our result must be in a one-dimensional subspace of V. And then we saw that earlier that any one-dimensional subspace of V has to be in this form, which is just some number scalar multiple of U. That brings us to our second point, right? So if TU is in the subspace capital U, that means TU, this operator multiplied by the vector, can also be represented by some scalar lambda multiplied by U, right? Because we know this thing is in capital U, and that's the definition of being in capital U, right? We are, they are a scalar multiple of U. So our goal here is we want to find the real numbers lambda and the vectors U such that this whole thing is true, right? Based on T, based on what type of operator we have. And that's the main idea of eigentheory, eigenvalues and eigenvectors. And actually, in fact, if this is true, then this number lambda is called the eigenvalue, and the vector U is called the eigenvector. Right. But next, we're going to look at definition of eigenvalues and eigenvectors so that we have a better idea. All right. So let's start by looking at definition 1, the first definition. A scalar lambda in R is called an eigenvalue of operator T that maps V to V if there exists a non-zero vector U in V such that T U is equal to lambda U. Okay, so let's do this. We have a map T that maps V to V, right? And then there is some U, some vector U in V, little u in V, right, in the first one. And then that is going to be sent to T of U, which is also in V, right? And then we want to find, we want to make this equation true. And if this equation is true, then this real number lambda is called the eigenvalue. Okay, so depending on what type of operator we have, we are able to find the u's and the eigenvalues that satisfy this equation. Okay, and here we also want u to be non-zero, right? If u is 0, then lambda can be anything, right? All right, so let's look at some extra work from earlier, so that let's say we want to find out what T of let's say Tx, right, where x is again some vector, right? Now, in order to evaluate this operation, most of the time we're going to find some matrix A to represent the operator for T, and then multiply that by the vector we have. Okay? Now, from earlier, we know if we perform the operator, it's the same thing as taking some scalar or eigenvalue multiplied by the same vector, right? So here, we can also say that AX is equal to lambda times X, right? Where A is a matrix and lambda is a scalar. All right, so let's look at this. T of Tx, that is our operator, or you want to operate the T on X, and that can be done by taking some matrix A that represents the operation on T, multiply that by the vector X. And from earlier, we know that this, the operator Tx, is also equal to just some scalar multiplied by the vector, so that we can write it as Ax is equal to lambda x. Okay. And now what I'm going to do is I'm going to move everything to the left-hand side, like this, right? Ax minus lambda x is equal to 0. Now the 0 here, keep in mind, it's still a vector. And I'm going to factor out the x to the right-hand side, right? This is a right multiplication, right? Meaning the vectors x are on the right. So I can write this as a minus lambda I multiplied by x is equal to 0 vector. All right, so here is something interesting. Notice that here I added an I which means the identity matrix, because lambda is a scalar. In order for two matrices to subtract, in this case, right, we want them to have the same dimension, right? So whatever dimension A is, that's the dimension I is going to be, right? Let's say A is n by n, then I is going to be n by n as well, right? So lambda I, this matrix right here, right? It's very interesting, right? So lambda I is basically a square matrix, right, with lambda on the diagonal, right, like that, right, and everything else is 0. Right? That's what we're talking about. Yeah. So, but if by looking at this equation, we can say this is a matrix equation where on the right-hand side we have 0. Right. So let's actually move on to our next definition before we keep on going with this part. So the general idea is if you can solve this equation, then we are able to find lambda and x. Okay, let's take a look at the second definition. Suppose lambda in R is an eigenvalue of A, right? So let's stop there, right? So lambda in R is eigenvalue of A. Okay. Whenever we see that, there is another piece of information we have, which is the second part of the definition. Let's take a look at that together. A vector x in V is called an eigenvector of A if AX is equal to lambda x, right? So eigenvalue has to match an eigenvector, right? In this case, our eigenvector is x, right? Is called an eigenvector if that equation is true, right? I'm gonna make it a little bigger. If AX is equal to lambda x, okay? So that is the definition for eigenvalue and eigenvector. In order to be an eigenvalue, it has to, you can find a non-zero vector such that Tu is equal to lambda u. That's from definition 1. And for eigenvector, suppose that we have an eigenvalue already, right? Then we need to find that vector x such that that vector satisfies this equation with the given eigenvalue. Now, of course, a lot of calculation can go into this, but we'll take a look at that just in a few minutes. Okay, now let's go back to the equation that we had earlier. A minus lambda I times x is equal to 0. Again, 0 vector. So what we have here is that lambda is our eigenvalues, right? And x is our eigenvectors. So what we have here essentially is that we want to find the null space of A minus lambda I, right? Remember the null space, right? Everything in the null space makes this equation true. Right? So we want to find the vectors x that satisfies this equation, and that x is going to be in the null space of A minus lambda I. Now again, of course, we're assuming that x is non-zero. If x is 0, then everything is easy. Okay. And then another way to look at this is the set of the solution that satisfies this. So let's say all x that satisfies the equation A minus lambda I times x is equal to 0 is the set, the null space of A minus lambda I. Okay, right? So everything in here satisfies this equation, and everything that satisfies this equation is in here. in this set, right? And we also have another name for that. It's called the eigenspace of A corresponding to lambda. Sorry about my writing, but you can read that in the notes just right above theorem 1. All right, so theorem 1 tells us our first way to find eigenvalues. Let's look at them together. Suppose T is a map from V to V, has an upper triangular matrix with respect to some basis of V. Then the eigenvalues of T consist precisely of the entries on the diagonal of the upper triangular matrix. All right, so let me give you an example. All right, so let's say my matrix is like this: 1, 2, 3, 4. And I have 0, 0, 0, 0, 0, 0, -1, -5, 4, 3, 1, 2. Right, something like this, right? This is called an upper triangular matrix, right? All the non-zero numbers are above the diagonal, and then everything below the diagonal are zeros. So what theorem 1 is saying is that our lambda, our eigenvalues, are the diagonal entries, right? 1, lambda 2, 2, lambda 3, 3, lambda 4 is 4. Okay, that's it. That's what theorem 1 is saying. Now, for the time being, I'm not going to go over the proof in details, but if you're interested, you can take a look at that in the notes or in the textbook. All right, so theorem 2, let's take a look at them together. If V1 up to Vr are eigenvectors that corresponds to distinct eigenvalues, lambda 1 to lambda n. So let's write it down first. So I have V1 up to Vr that corresponds to lambda 1 up to lambda r. Now notice that here they say that they're distinct. That means lambda I cannot be equal to lambda j for any different ij. All right. They are eigenvalues and eigenvectors of an n by n matrix A. Then the set V1 to Vr is linearly independent. Right. Then the set V1 up to Vr are linearly independent. Okay, so this is what we can assume. And again, the proof is quite long for this one, so I'm not going to go over this. Maybe I can make a separate videos for the proofs. But so far for now, we are not going to worry too much about the proof, but understand what the theorems are saying. Okay, so let's start with theorem 1 again. Right? Theorem 1 says if you can make a matrix into upper triangular, then the diagonals are your lambdas, right, are your eigenvalues. All right, theorem 2 says if you have r many distinct eigenvalues that correspond and with the corresponding eigenvectors, then those eigenvectors, this collection of all the eigenvectors, is going to be linearly independent. All right, now let's look at our first corollary. So corollary is just like a mini theorem or something that results from a theorem. Right? Let's take a look at that. Each operator on V has at most dimension of V distinct eigenvalues. All right, so basically what this is saying is that the eigenvalue of an operator cannot exceed the dimension of the subspace that you're working in. Right, so for example, if I have T mapping from V to V, right, where V is a subspace of, let's say, R3, right? And when, let's say we are guessing that, we're assuming that dimension of V is 3, right? Therefore, you can only have at most 3 distinct eigenvalues. Right. Sometimes you will have repeated eigenvalues, but we're just saying at most we will have 3 distinct eigenvalues. Okay? And the proof of this is actually using theorem 2, right? If you look at the proof, I'm just gonna briefly talk about this. Right. So let's look at the proof of the corollary. Let T be a map from V to V be an operator. Suppose lambda1 to lambda m are distinct eigenvalues of T. Then let V1 to Vm be the corresponding non-zero eigenvectors, right? So these eigenvectors V1 to Vm, they are the eigenvectors to the eigenvalues lambda1 to lambda m. And from our last theorem, we know that the collection V1 to Vm, they are linearly independent. That means none of them can be written as a linear combination of the other, right? Then that brings you to different distinct eigenvalues. And that's why we can conclude the last part of the proof. Thus, m is less than or equal to the dimension of V as desired, because they are linearly independent inside the subspace V. All right, example 1. Is lambda equal to 3 an eigenvalue of the matrix A? Right? If so, find one corresponding eigenvectors. All right, so let's focus on the first part first. Is lambda equal to 3 an eigenvalue? All right, so let's go back to definition. In order for lambda equal to 3 to be eigenvalue, we want non-trivial solution, meaning x non-zero, right? Non-zero vector, such that ax is equal to 3x. All right, so we want to show that this equation is true for some non-zero x. Right? If we can show that, then we can say that yes, lambda equal to 3 is an eigenvalue. All right, so to do that, first we want to look at ax is equal to 3x, and then I'm going to move that over, right? X minus 3x is equal to 0, and then a minus 3I times x is equal to 0, right? Backed into this form, which we are very familiar with, right? We want to show that the null space has non-zero vector, meaning we want this to be true for some non-zero x. If we can show that the solution to this is non-trivial, then 3 is going to be an eigenvalue. Right, so let's do that. A minus 3I is equal to this, right? So we have A, and this is 3 times the identity matrix, right? The identity matrix in this case is a 3 by 3 with diagonal being all ones, and then we multiply 3 to the identity, so all the ones becomes a 3, and then we will have this, right? So our goal is to take this matrix, right? That's your matrix right here, and try to solve this matrix equation. Okay, and we have this, right? We want to solve this equation, and this is the matrix that we got from earlier, right? A minus 3I is of this form, and then we put them in augmented matrix form and try to solve for x. All right, and when you put it in reduced row echelon form, we see this, and we can tell clearly that we will have non-trivial solution because we have 3 variables in this case, right? Let me show you what I'm talking about. Right, so from the first equation, we can say that x1 minus 3x3 is equal to 0, and x2 minus 2x3 is equal to 0, right? So in this case, we actually have a free variable, which is x3, right? To rewrite this, we can say that x1 is equal to 3x3, and x2 is equal to 2x3, right? So any x3 value or any vector that satisfies this system will be our eigenvectors, right? So in this case, yes, x3 is going to be our eigenvalue. And to find an eigenvector, all we need to do is just pick any x3 in and then find our x2. So let me show you how this is done. All right, so if we pick x3 to be 1, that means x1 is 3, right? Because 3 times x3 is 3. And then x2 is 2 times x3, which gives us a 2. All right, next, we want to see if this is true. If we multiply a by x, does that give us 3x? So let's actually check 3x first, right? 3x is going to be 3 multiplied by 3, 2, 1, which gives us 963, right? That's the right-hand side of the equation. And let's check the left-hand side of the equation, see if that's true as well. All right, so we have our matrix A and our eigenvector x. Right, let's see if we multiply this, if we get the same thing as 3x, which is 963 from previous page, right? We want to get this, right? So let's take a look. All right, and in fact, if you do matrix multiplication, right, we did that, I think, when we were still in school, right? So we multiply that. Actually, no, there was a video on how do you multiply matrices and vectors, right? So then we get this, which is equal to 3x, and we can say yes, lambda equal to 3 is an eigenvalue, and one of the eigenvector is going to be 3, 2, 1 is an eigenvector. Right? Now, of course, you can find, you don't have to use x3 equal to 1 to find your eigenvector, right? You can use -1, you can use 2. Now, one thing you don't want to do is pick 0. Right? If you pick x3 equal to 0, then everything is going to be 0, which is the trivial solution. And we don't want to use the trivial solution when we are looking for eigenvectors. All right, example 2. Our goal is to find a basis for the eigenspace for this matrix, and we're also given 2 lambdas. Now, if you go up to your notes earlier and look at the part right above theorem 1, so the eigenspace is also the null space of A minus lambda I, right? So basically what we need to do is we just need to find a eigenvector that corresponds to lambda equal to 1 and another eigenvector that corresponds to lambda equal to 5, and the collection of these two vectors will be your basis for the eigenspace. And from theorem 2, I think theorem 2 earlier, we know for sure that distinct eigenvalues will give us distinct eigenvectors, right? So distinct eigenvalues will give us linearly independent eigenvectors, right? So let's do that real fast. Okay, so first I'm gonna work with lambda equal to 1 first, right? So A minus 1I is going to be 7, 4, -3, -1, minus 1, 0, 0, 1, which is 6, 4, -3, -2. All right, and then use that 6, 4, -3, -2, 0, 0. Try to solve this. Right. Let's say multiply by 1/2 and then add to that. So 6, 4, 0, and then that's gonna give you 0, 0, right? And then we can divide that a little bit. 3, 2, 0, 0, 0, 0, right? So divide row 1 by -2, right? Here we have 3x1 plus 2. Actually, let me move it up a little bit, right? So this part, the first row, tells us that 3x1 plus 2x2 is equal to 0. That means x1 is -2/3 of x2. All right, so let's say let x2 be 3, then x1 will be -2, right? So have our first eigenvector right here, -2 and 3. Right? So this eigenvector, let's call that V1, corresponds to lambda 1. Right? Because we got this by picking lambda equal to 1. And let's do another one where picking lambda equal to 5. All right, so here we go. A minus 5I. We have 2, 4, -3, -6. All right, and then let's look at the augmented matrix. 2, 4, -3, -6, 0, 0. Right. So you can see that if I multiply the first row by 3/2, then I get the exactly opposite of this. And so I can get 2, 4, 0, 0, 0, 0, and then maybe divide that by 1/2. Multiply that by 1/2. Get 1, 2, 0, 0, 0, 0. All right, and then from here again, our first row, we get that x1 plus 2x2 is equal to 0. That means x1 is -2x2. All right, and then we can do the same thing. Let x2 be 1, then x1 will be -2. And here is our second eigenvector, -2 and 1, corresponding to lambda equal to 5. All right, so combining both of them together, right, we know that V1 was -2, 3, right? -2 and 3. And then V2 is -2 and 1. Now, notice that they are linearly independent, right? It doesn't matter. You cannot cancel them or try to get them equal to 0 with a non-trivial solution, right? So this is your basis for the eigenspace right here, right? So we can say that the eigenspace. Let me open up a new page. Okay. So we can say that the eigenspace for A is the span of those two vectors, -2, 1. And what's the other one? -2, 3. And -2, 3. Okay, there you go. That's example 2. Now, it doesn't matter, for example 2, it doesn't matter what value of x2 you pick, right? Here I'm just picking some nice value that will help me with that calculation. For example, I pick 3 here so that it reduces with the denominator. For lambda equal to 5, I basically pick 1 because it's easy to work with. It doesn't matter which one you pick, because based on the value you pick, they are going to be just scalar multiple of these eigenvectors that we have here. No, they're still basically the same thing. All right, example 3, find the eigenvalues of the following matrix. All right, I'm going to give you guys a few seconds. If you want to pause it, right, you can pause it, but take a few seconds and see if you can figure this out. All right, if you need a little hint, this is a triangular matrix. All right, and from one of the theorems that we saw, if you have a triangular matrix, right, this will be a lower triangular matrix, right, where all the non-zeros are below the diagonal, right? And it has the same property, right? All the entries on the diagonal are going to be your eigenvalues, right? So lambda 1 is 4, lambda 2 is 0, lambda 3 is -3. Voila, that's it. All right, so this one is actually a pretty interesting one. Example 4, where you're given this matrix that it's 3 by 3 and all the entries are 5. So one thing we need to check, we need to know is that this thing is not invertible, right? Because all the columns are linear, they're basically the same, right? All the columns are the same. They're not invertible. So one of the property that we didn't talk about in this case is if it's non-invertible, then the eigenvalues is 0, right? So we will have an eigenvalue of 0. That means we want to find the eigenvectors, we want to find a x equal to 0x. Now, of course, we know that 0 multiplied by any vector is going to be 0, right? But also we want a multiplied by x to be 0, right? So how do we pick x so that this left-hand side is 0? Of course, we don't want to pick 0, the 0 vector, right? If you have 0, 0, 0, then defeats the purpose of looking for eigenvectors, right? So let's look at what we're doing when we multiply the matrix by just some vector, right? And I'm going to multiply that by, let's say, x, y, z. Okay, and this is what we have. All right, so this is what we have. We just have 5x plus 5y plus 5z for all three rows. And what do we want them to be equal to? Right, this is the left-hand side, right? That's the left-hand side of the equation. Now, the right-hand side, we want them to be 0, 0, 0, right? Now, since they are all three rows are the same, we can just focus on one row, right? We want 5x plus 5y plus 5z to be 0. And if I divide everything by 5, I get x plus y plus z is equal to 0. So what does that mean? It means we can pick any vector x, y, z, so that when I add these three entries together, we get 0. Right? Let me give you guys a few examples. 1, 0, negative 1. Right? When I add x, y, and z, I get 0. Okay, satisfy this condition means this is going to be an eigenvector. Let's do another one. 1, 2, 3, 2, 3, 4, negative 3, 5, 7. Right? I'm just gonna go a little larger, right? This also works because when I add these three numbers together, I still get 0. Now, of course, you don't have to go this far, right? Another one, nice one would be 1, 1, negative 2. Right? When you add up the three entries, you get 0, which satisfies this part, right? That means when you take any of these three vectors and multiply by the matrix A, you will get 0, 0, 0, 0, right? So you can try a couple of different things. There is another eigenvalues for this matrix, right? Let's see if you can figure it out. And of course, the corresponding eigenvectors as well. All right, example 5. Suppose A is an n by n matrix. Mark each statement true and false. Justify. All right, so let's look at number 1. If ax equal to lambda x for some scalar lambda, then x is an eigenvector of A. So think about this for a second. All right, so this is only true if x is non-zero, right? If x is a non-zero vector, right? If x is a zero vector, then it defeats the purpose, right? 2, if v1 and v2 are linearly independent eigenvectors, then they correspond to distinct eigenvalues. So one of the theorems earlier, we said that distinct eigenvalues will give us linearly independent eigenvectors, right? So the converse is true, but this statement is actually false. Right, if you look at example 4, you can see that we have eigenvalues of 0, but then we get we can come up with many linearly independent vectors. Right. 3, the eigenvalues of a matrix are on its diagonal. Well, this is false. Right? It's only true if the matrix is triangular. Only true if matrix is triangular. Or 4, an eigenspace of A is a null space of a certain matrix. Yes, true. Right? And to be a little more specific, it's a null space of the matrix A minus lambda I. Right? Remember this? Right? We can, to find the eigenspace, we look at the null space of A minus lambda I x equal to 0. All right, so example 6, show that lambda is lambda is an eigenvalue of A if and only if lambda is an eigenvalue of the transpose of A. So transpose again means just when you the columns becomes the rows and the rows becomes the columns of A. So here we will need one property that we haven't talked about, is that if lambda is an eigenvalue of A, then the determinant of A minus lambda I is equal to 0. Right? So here what we can do is that, okay, we are going to start by looking at the determinant of A transpose minus lambda. Now that is also equal to the determinant of transpose of A minus lambda of the transpose of I. Now I is equal to its transpose, so we can do that. And that is also equal to the determinant of A minus lambda I transpose. And we know that determinant actually is preserved under transpose, so this is actually equal to the determinant of A minus lambda I, which is equal to 0. Hence, we can say that lambda is an eigenvalue of the transpose of A. Right? And then the reverse is the same, right? You can start with this and then going back to the transpose. All right, example 7. Consider an n-line matrix A with properties that the row sums all equal the same number S. Show that S is an eigenvalue of A. Right? So A, let's say we have all right, let's say A11, A12, A1n, and then this is AN1 to ANN. Right. All right. So the property that we have is that if we take I going from 1 to n of some row, let's say some row m, right? You always get S, right? The sum S. Yeah, so this is particularly nice, right? So we're going to show S is an eigenvalue. And this is very easy, right? If you want to give it a try, you can pause the video, but we want to show that A times X is equal to S times X. Right? In this case, I'm going to let X be an n×1 vector with all ones. Right? So let's take a look at this. A times 1, 1, 1, dot, 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 dot. Right? This is just going to be a vector of A11 plus A12 plus dot, 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 up to A1n. Right? And then same thing for these, right? This is going to be AN1 plus dot, 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 ANN, which is going to be just a vector full of S's, right? And by definition of the eigenvalue, right, S times X, S times all my ones, right? And that gives me the same thing, right? So if I pick my eigenvector to be all ones, then it's going to satisfy this eigenvalue of S because of the property of this matrix, right? All the entries in the row add up to be the same thing. All right, and example A is pretty easy, right? You combine the result from example 7 and example 6, right? So first, we have a matrix A that all the columns add up to the same thing, right? So A means all columns have same sum. All columns have same sums, right? Right, then we know that the transpose of A will be all rows have same sum. Have same sums. Okay. Now we know that if all rows have same sum, which is S, then we know that the eigenvalue is S from example 7. And from example 6, we know that A and the transpose of A have same eigenvalue. Right? Then combining this, we know that the transpose of A and A will have the same eigenvalue, which is lambda S, which is S, right? Therefore, A has eigenvalue lambda equal to S, right? So example A, there is no proof needed, right? All we're doing is using the result from example 6 and example 7, right? Example 6 tells us that the eigenvalues are the same between a matrix and the transpose of that matrix. Example 7 tells us that if every row has the same sum, then that sum is going to be your eigenvalue, right? And combining these two results, we can prove example 8 real fast. All right, and that is all for 5.1. Thank you guys very much, and have a good day.